Um, Hi. Good morning, everyone. Welcome to 11785 Introduction to Deep Learning. I'm one of your TAs, Bhuvan, and this is Soumya. And today we would have the first recitation, which is on writing your first deep learning code. So there's the overview of the recitation. So before we can actually start writing the code, or before we can actually start writing our first deep learning code, we need to know what neural networks are and what deep learning is. So for the first 10 or 15 minutes, I will give a very brief overview of what neural networks are. This would be covered in detail in the next 3 lectures. So I will give a very mechanical overview of how a neural network actually computes an output given the input and what a neural network exactly is. So we begin with the perceptron, or the so-called artificial neuron. It is the basic computational unit in a neural network, and it has these d real-valued inputs. You can view it as a vector, a real-valued vector. Then for every input, it has a weight, which is also a real number, and then it has a bias. So as you can see in the first half of the neuron, it basically computes a sum. So what it does, it computes a weighted combination of the inputs plus the bias. And then it applies an activation function, which is the G function here, which is finally the output of the perceptron. So just to reiterate, it is the basic computational unit, and the inputs combine linearly in a perceptron. And this is the mathematical formula of what a perceptron actually computes. So like I said, it computes the weighted sum plus the bias, and then it applies the activation function, which is G, which we'll see later what G is usually in neural networks. So why is a perceptron actually interesting? What can we actually do with a perceptron? So like we saw, when suppose here the activation function is a step function. So g of x would be 0 if x is negative and 1 if x is non-negative. And like, let's suppose that we have 2 dimensions, so we have x1 and x2. And so we can see that when w1 x1 plus w2 x2 plus the bias is 0, that's the equation of a line in 2 dimensions. And in higher dimensions, it is what is known as a hyperplane. So basically, a perceptron is a linear classifier. It draws a straight line, and then on one side of the line, it classifies everything as 0, and on the other side, it classifies everything as 1. So that's good. That's not very interesting. I mean, we want to have more powerful models of computation. So what can we do? So before that, I'll just talk a bit more about activation functions. So here it's a step function. It is a hard jump from 0 to 1. But we can have different activation functions. So the first one is the sigmoid function, which is like a smoothened version of the step function. Then you can have the hyperbolic tangent function, which is basically a scaled version of sigmoid. It goes from -1 to 1 instead of 0 to 1. And then you have the ReLU, or the rectified linear unit. And we'll see later in lectures how the different activation functions actually affect what we do with the neural networks. So like I said, perceptron is just a linear classifier, and we want to have more powerful models of computation. We want to classify more interesting, maybe nonlinear decision boundaries. So for that, we can basically have a network of different perceptrons, and this is called a multilayer perceptron. So the first perceptron, the first MLP here has only one hidden layer, and the second one has 2 hidden layers. And these are called hidden layers because we don't actually see the output. We don't actually see the values of the neurons in the hidden layer. We only see the input and the output. And then for every multilayer perceptron, we have 2 important parameters, hyperparameters associated with it. Those are the depth and the width. And the depth is basically the number of hidden layers in the neural network. So on the first neural network, we only have a single hidden layer, and on the second one, this one, we have two. And apart from the depth, we have the width of the neural network, which is basically the number of neurons in the hidden layers, in one particular hidden layer. So like I said, this is a fully connected multi-layered network of perceptrons. We call it fully connected because each perceptron in a layer is connected to all the perceptrons in the previous layer and in the following layer. And it turns out that it is much more powerful than a single neuron, and it can represent any function. And you will see in lecture 3, this is actually known as the universal approximation theorem. And this is the main idea behind why neural networks are so powerful. So an MLP is now basically just a function which takes an input and computes an output. And so these are some different examples of what our function can be. So the first one takes in as input a voice signal, and then outputs the transcription. So this is used in maybe Siri or Google Translate. Then the second one takes in as input the image and outputs the text caption. And the final neural network takes the game state as an input and outputs the next best move. So if you might have seen the AlphaGo neural network, which beat Lisa doll, that behaves something like this. Now I'll delve into more depth about one particular example. So suppose we want to classify cats and dogs. So you can have a neural network like this, where you have the input, and each value in the input layer would actually be a particular pixel value of the input image. And in the output layer, you can have two neurons. So if you feed in a dog image, the bottom neuron will light up, and the top one will be 0. If you have a cat, then the top neuron will be 1, and the bottom neuron will be 0, something like this. So we now know that MLPs can represent almost any function. But how do we actually learn? How do we actually learn that function? How does the MLP actually represent it? So before we begin, what exactly are we learning? So as we saw, it is basically a function which has many different parameters. And what exactly are the parameters of the neural network? Those are the weights and the biases of the different layers. So as we saw in a perceptron, we have a weight for every single input. And so in an MLP, for every layer, we put the weights in the matrix and the biases also in the matrix. And each column of the matrix would be the set of weights associated with the particular perceptron. So does anyone have any questions till now? OK. So again, I'll return back to the example of suppose we want to classify cats and dogs. How we do that is basically by providing many different input and output pairs. These are the so-called training examples. And we basically give these training examples, and we nudge the parameters in one particular direction so that it basically represents that function. And our aim is to match the training data as close as possible, and hope that if our training is correct, then if we give in a new example, the network will also be able to classify that correctly. And for that, we need a quantification of an error term. So that error term would tell us how far we are from the actual function that we want to represent. So now in more abstract terms, suppose this is the actual function which we want to learn. We basically have these samples, xi and yi, and we want to estimate the parameters from these samples. So then we have this error term, and this error term is basically the sum of the error terms for every different example that we have in our neural network. So this div, this is the divergence between the network output and the desired actual output, and we basically take the mean, and we want to minimize this loss term. So we want to find the set of weights such that this such that we minimize this. And this capital W is the set of parameters, and this is basically all the parameters of the neural network. So that includes all the weights and the biases of each layer. Any questions? Okay. So now the only thing which is left is how do we actually optimize the parameters so that the error is minimized. And we do that by something which is known as gradient descent. So let's suppose, for example, that we only have a single parameter in the neural network, and we plot the loss term or the error term as a function of the parameter. So if you notice, if the slope at any particular point is positive, is negative, then you would want to increase your W so that if you increase your W, then the loss term would decrease. And similarly, if the slope is positive, like here, if you decrease W, then your loss term would decrease. So basically, you want to go down into the valley, and this is the idea behind gradient descent. And this is the same figure, but in 2 dimensions. So now instead of slope, we have the gradient vector. And it turns out that in the direction of the negative of the gradient vector, or in other words, if you go opposite the gradient vector, then loss term decreases the most or the fastest. So now this is basically a recipe for optimizing or for learning any arbitrary function if you have a neural network. So you first initialize all the parameters, and then you want to perform gradient descent until convergence. So for that, you compute the loss, and the equation for the loss we've already seen in the previous slides. Then you compute the gradient of the loss with respect to the parameters. And this is nothing but just the derivative of the loss with respect to each individual parameter of the neural network. So that includes each weight of every layer and each bias of every layer. And then finally, you want to update the parameters. So this is the update equation for gradient descent. You subtract, you basically, so eta is the step size. So you take a small step opposite the direction of the gradient, and that is a new weight. And this is the same thing in the scalar form. So for every parameter and for every weight and bias in the neural network, you want to take a small step opposite the direction of the gradient. And so one important thing is that gradient descent does not guarantee that you reach a global minimum. It only guarantees that you reach a local minimum. So are there any questions?
Could you talk a bit louder, please?
OK.
Thank you.
So now we will actually begin with the actual recitation, which is writing your first deep learning code. So let's start with deep learning frameworks. So if you've already finished homework 0 or started working on homework 0, you would have worked with NumPy. And basically, deep learning frameworks provide similar computation as NumPy, but with added GPU support so that you can parallelize your computation and make it faster. And they also provide some nice neural network layers. So you don't basically have to write everything from scratch. There are many things which are already coded for you. And most importantly, they provide with something called as automatic backpropagation, which we will see later. And Recitation 2 is actually basically on that, but you will see later in lectures what backpropagation actually is. So we will work with Pytorch throughout this whole course. Basically version 1.3. you are free to use any deep learning library that you want to, but the TAs would only be able to provide support with Pytorch in the recitations and on Piazza. So let's begin with tensors. So tensors are very similar to NumPy's n-dimensional arrays. You would have worked with them in Homework 0, and they provide basically all the same features that NumPy provides. You can convert a tensor to NumPy arrays, and you can also convert a NumPy array to a tensor. You have all the basic functions such as exponentiation, sum, and matrix multiplication. And so the main difference between a tensor and a Pytorch tensor and a NumPy array is that tensors can be used on the GPU. And that is the main advantage of tensors. So let's begin with the difference between CPU and GPU operations. So Pytorch has support for NVIDIA GPUs, also CUDA. So CUDA is basically the parallel computational library for NVIDIA GPUs. And to copy a tensor to a GPU, you just have to call the .CUDA function. And to copy it back to CPU, you have to call the .CPU function on the tensor. And one important thing to keep in mind is that, as I already told you, NumPy arrays are only supported on the CPU. So if you want to convert a GPU tensor to a NumPy array, you can't directly call .NumPy. You have to transfer it to the CPU first, and then you can call .NumPy. And also, if you have two different tensors and you want to do some computation on both of them, you have to make sure that they are on the same device. So either both of them should be on the CPU or both of them should be on the GPU. You can't mix operations between two different devices. So as you can see in this code snippet, if y here is a GPU tensor, and if you do a matrix multiplication between x and y, then that will basically throw up an error. So these are some small things that you want to keep in mind while doing your assignments. And so typically, you can write your code in such a way such that it is device agnostic. So it would run both on the CPU and the GPU. There are many different helper functions for that. In the full code example, as we will see at the end of this recitation, we will show you some ways as to how you can use some of the helper functions in Pytorch to actually write your code in such a way. On this slide, this snippet has one example. So you can basically check if CUDA is available. It means if there is a GPU on your device, then you would transfer your tensor to the GPU and then do some calculations. And at the end, you would copy it back to the CPU and then convert it to NumPy or whatever. And now we will see what automatic backpropagation actually is on a high level. And that is one of the main reasons why we use such deep learning libraries. So if you remember in gradient descent, one of the steps was you want to compute the gradient of the loss function with respect to every parameter of the neural network. And so backpropagation is basically a way of computing those gradients in an efficient way so that you don't have to repeat you don't have to redo the calculations. And it turns out that Pytorch provides us with this. Pytorch automatically can compute all the gradients for us. We just have to write how to compute the loss. And to do that, you have to call the .backward method. So if you want to compute the gradients, whenever you make a tensor, you want to provide this argument, requires grad. So when you do requires grad equals true, you're basically telling Pytorch that you want to keep track of the gradients. Here, it fails because torch.arange gives you a tensor which is of type long. And so it can only contain discrete values. And for discrete values, you cannot compute a gradient. So for that, you actually have to convert it to a float tensor, and keep requires grad equals true. Here, x is a tensor which has values 0, 1, 2, 3. And then I suppose I square x and then compute the sum. And then I call backward on y. So the gradient here on line 7, you can see the gradient of dy by dx, and y is basically x squared, should be 2x. And when we do y dot backward and we print x dot grad, which is the gradient in x, you can see that it's basically 2 times x. So in this snippet, we never actually wrote that we want to compute 2 times x. We never actually had to hard code that the gradient of x squared is 2x. Pytorch did it automatically for us. And this is a very small example, but when you actually write your own whole neural network, you will see how useful this automatic backpropagation actually is. So now let's begin with neural network modules. So as we already saw, it's just a function which takes as input some values and outputs some values. And it is parameterized by the weights and the biases. So Pytorch provides these different layers of neural networks, which are basically the implemented subclasses of torch.nn.module. And if you want to make your own neural network or make your custom neural network, you would want to inherit from this class. So we'll see some small examples here. Suppose we have already made the neural network, then the forward function takes as input the x and outputs the value depending on the parameters of the neural network. And you can view all the parameters by calling the dot parameters method. So now we will actually build a toy neural network using Pytorch. So here we first inherit from the nn.module class, and let's say we want to have two layers. So we have 2 sets of weights and biases for each layer, and then in the forward method, we have one input which is x. So first we compute the linear combination for the first layer, and then we would apply the activation function for that. So here the first line is basically a matrix multiplication between x and the layer 1 weights. So as we already saw, we keep the weights in a matrix so that if we do a matrix multiplication between x and the weights and the matrix, you get the linear combination, because matrix multiplication is nothing but the inner product between each column of the matrix and each row of x. So each one is basically just the linear combination of the first hidden layer, and then we do then we have the ReLU activation function, which we saw in a previous slide. So here h1 underscore act would be 0 for all the negative values, and it would be the identity function for all the positive values. And then on that, we apply the second layer weights and the biases, and then we return the output. So this is not a very good way to write a neural network in Pytorch, because you're basically coding everything from scratch. Pytorch already gives you many different helper functions which you would want to use. So this is another way of writing the same function. So instead of having layer 1 weights and biases and layer 2 weights and biases, you just now have a single linear layer. And linear layer basically does a linear transformation, so you don't actually have to you don't have to initialize your different parameters, or everything is done by the linear layer. And then layer 2 is the sigmoid activation function. So again, you don't have to actually write your own activation functions. Pytorch gives you many different kinds of activation functions. It also gives you the ReLU. And then layer 3 is the same which converts the hidden layer to the output. And to actually write the forward method for this, you just have to pass it through the different layers. So first you pass it through layer 1, then layer 2, then layer 3, and finally you return the output. So as you can see, this is a much more cleaner way of writing a neural network. And as you work on your assignments, you would this is basically the structure of how you would write your neural network. And then another thing to note here is that nn.linear and nn.linear is itself a smaller neural network. So when you put a smaller nn.module inside of another nn.module, then all the parameters of that smaller network get absorbed into the bigger network. So if you actually look at the parameters of this neural network, it would contain the parameters of both the linear layers. And we will see why it's important when we actually optimize the neural network. So does anyone have any questions? Okay. So this is a very simple multilayer perceptron because the input just passes from one layer to the next one. So Pytorch also provides us with a sequential module. So you just put your different layers in that. And then for sequential, you don't even have to write a forward method. If you just give it the input, the forward method is implicit and sequential because it passes the input vector or the input tensor through each layer sequentially. And for homework 1, part 2, this is basically what you need. Again, we can, when you write your own neural network, these are just some tricks. Like you don't want to hard code the values. So here, ReLU MLP is a class which returns a neural network, and it takes in as input a list of sizes. So these are the sizes of the different hidden layers, and you basically append a linear layer in the layers array, and then you return a sequential network depending on the input which it got. And then you can have another bigger MLP, and in that you can have 2 different ReLU MLPs. So this is something like a tree structure. So the parameters of the linear layers would be absorbed into the parameters of ReLU MLP, and the parameters of ReLU MLP would now be absorbed into the parameters of the bigger MLP. So now when you actually do gradient descent on the bigger MLP, all the parameters in the other layers would automatically be updated. So now that we have already seen how to define the architecture of the neural network, we will now see how we actually optimize and compute the loss and optimize for it in Pytorch. So Pytorch also provides us with many different kinds of losses. You will learn more about different losses in lectures 3 and 4. So here we are using the cross entropy loss, which is basically a loss which we use for categorical functions. So like in the example which we saw before, if you want to classify cats and dogs, we would use a cross entropy loss. So to actually use a loss, you would compute the output from the network. So this is the actual output of the network, and y is the desired output of the neural network, and the loss is so you initialize the cross entropy loss, and to compute the actual scalar value of the loss, you provide the network output and the desired output, and that is your loss. So here we are just making some dummy tensors and some dummy target values, and here the loss is 2.4. So to actually optimize for the loss, we use the optimizer class in Pytorch. and it contains many different algorithms for optimization. So we saw one such algorithm, which is the vanilla gradient descent, where you compute the gradient and then you take a small step opposite to the gradient direction. Here, this is torch.optim.sgd, which is the stochastic gradient descent. You will learn more about this in lecture 3. So to initialize the optimizer needs to know what parameters it has to update, and also the learning rate. So the learning rate is basically the step size, the eta which we saw in the previous slides. And to actually make a step opposite to the direction of the gradient, you just do optimizer.step, and it automatically updates all the parameters of the neural network. So this is a small training loop, and this is basically the code of what I showed you in the slides of gradient descent. So here I do this for 100 iterations. I compute the output of the network, then I compute the loss, and then loss.backward is basically backpropagating the errors, and it computes the gradients of the error with respect to every parameter. And finally, I do optimizer.step. So that takes a small step opposite to the direction of the gradient, and hopefully that would decrease the loss a little bit. So one thing to keep in mind is that when you do loss.backward, in Pytorch, the gradients accumulate. So if you have already done loss.backward and you do loss.backward again, then those gradients would be added to the previously calculated gradients. So at every iteration, you would want to do optimizer.zeroGrad. It basically just clears the gradients of every parameter, and it sets them to 0. So now we move on to saving and loading. So it's very important that while you'll be working on your homeworks, you might have already seen in Recitation 0e how to use tmux when you're working on AWS EC2 instances. But even then, you would want to keep saving your weights and biases as you're training, so that if suppose something happens and you're training, maybe there's a bug in your code and your code crashes, so you would want to have a set of those weights and biases so that you can load them at a later time, and then continue your training from that point. So to save the weights of the neural network, you just have to call these helper functions, torch.save the state dict of the neural network, and similarly to load, you just want to load from the file which you have saved your weights and biases into. And now I will go through some of the common issues that you might encounter while you're coding in Pytorch. So the first one is don't mix CPU and GPU operations, because these reside in 2 different devices and 2 different memories. So you can't mix operations between the 2. Either put everything on the GPU or on the CPU. And then this is also a very common error. You would want to make sure that the dimensions of your tensors match if you're doing matrix multiplication or any other operation. And finally, the star operation is not a matrix multiplication. It is just the element-wise multiplication. So here, X is basically a 2x2 matrix of 2s, and Y is a 2x2 matrix of 3s. So X times Y is basically 6, but the matrix multiplication of X and Y is the actual matrix multiplication. And then another operation in Pytorch is view. So in the view function, you can give different dimensions to a tensor. So here, X is basically a 2x3 tensor. And if you do dot view, the underlying data is the same. It's just that the dimensions change. So here, if you do x.view 3x2, then the order of the elements would still be the same, but the dimensions would be different. And this is not the same as taking the transpose of x, because in the transpose, you actually have to shift the elements across a diagonal. So here, the first tensor is the transpose, and the second tensor is the result after taking view of 3 by 2. And then one more thing to keep in mind is that your memory in the GPU is limited, and it can only hold a certain amount, a certain number of parameters and data. So here, I'm making this really big neural network, which has these many linear layers, and each linear layer has 2048 neurons. So the number of weights in a network, in a linear layer, is basically the product between the number of neurons in the previous layer times the number of neurons in the next layer. So here, the number of neurons would basically blow up, because for every layer you would have 2048 times 2048 neurons. And then my data x is is also 2048 dimensional, and the size of the batch is 256. So the batch size is the number of input points that you feed into the neural network at one point. And in Pytorch, the first dimension of the data is always the batch size. So here I'm keeping a batch size of 256. And when if I try to run this code, and if I do net.cuda and x.cuda, I would probably get a CUDA memory error, which basically means that you have too much data and too little GPU space. So if that happens to you, and that will happen to you, some things you can do is have a smaller batch size, and maybe check if there's a memory leak anywhere, clear your caches. Pytorch usually does a very good job of making sure there are no memory leaks, but still, if this happens, make sure there are no memory leaks. And then some other small bugs which can be hard to find. I mean, this is not very hard to find, but here I have a network which the input size is 4 and the output size is 2, and my x tensor is basically a 4-dimensional network, a 4-dimensional tensor, and the batch size is 1. But if I do net of x, which is basically calling the forward method of net on x, it would throw me an error, because the neural network expects tensors of type float, and here x is a tensor of type long. So always make sure that your inputs are of type float. If I do x.float and then print x, then x would basically be an object be a float tensor, and then this error would go away. Then this is another bug which is very common. So here I'm making another neural network module, and I'm making an array of hidden layers. And in the hidden layers, I append a linear layer of size 128 by 128. So there is actually a very serious bug in this code. And the bug lies in the init function. And it lies in the way that I have written self.hidden. So as I told you before, in a neural network module, if I have a hidden layer or sequential layer, then the parameters of that layer or the parameters of that submodule would be absorbed into the parameters of the bigger neural network. But here, that would not happen, because self.hidden is just a normal Python list. So if you actually optimize this neural network, if you call optimizer.step, the optimizer would not know that the parameters of each individual linear layer are actually parameters of the bigger neural network also, and those parameters would not be updated. So to solve that, we just add one more line, and we keep all the linear layers in the hidden array, in the hidden list, into an nn.module list. So when you use any nn.module list class or nn.sequential class, then that tells Pytorch that all the parameters of every layer in that list should be absorbed into the bigger neural network. Yeah.
Why would you use nn.module list as opposed to nn.sequential?
Okay, good question. So the question was, why would I use nn.module list as opposed to nn.sequential? And in this example, I would actually want to use nn.sequential because in the forward method, as you can see, I am just computing the output sequentially after every layer. So the main difference between nn.sequential and nn.module list is that in nn.sequential, the hidden layers are cascaded one after the another. So you don't have to write the forward function for that. And you can't actually view the intermediate outputs. You just give the input, and you see the output of the final layer in nn.sequential. On the other hand, in nn.module list, you have to iterate through every hidden layer. So in this particular example, nn.sequential makes more sense. But in some cases, you would want to use nn.module list because you would actually want to use the intermediate outputs in some different way. And that you cannot do with an nn.sequential.
What do you mean by parameters being absorbed into a higher neural network?
OK. So the question was, what does it mean by the parameters being absorbed into a higher neural network? So for that, I would go back to the optimization slide. So when you initialize your optimizer, you do net.parameters. And the dot parameters method returns all the parameters of the neural network. So Pytorch finds the parameters of the neural network as basically parameters of every sub nn.module inside your network. So again, in this code is buggy because the nn.linear layers are inside of a list. And Pytorch cannot find those parameters if they are inside a plain Python list. But if they are actually normal hidden layers, such that, for example, in this code, self.final layer is a linear layer. So Pytorch would be able to find those parameters. To tell Pytorch that these parameters also have to be optimized, you have to wrap them either inside of an nn.sequential or nn.module list. OK, any other questions? OK. When you're working on your assignments, your code would probably not work on the first go. So these are just some tips on how you would want to debug your code. So of course, always try to figure it out by yourself first. Just rereading the code many times, or maybe sometimes, can help a lot. If you know how to use a debugger, you can use that. Then you can always search online, because all the errors that you would run through, someone else would have already gone through that process before. So you can go on to Stack Overflow. You can always use Piazza. We are always there to help you. And of course, you can always come to office hours. The schedule of the office hours would be posted in the next few days. And from the next week onwards, we would start having regular office hours. And now we will go through an actual a neural network example in Pytorch. And for that, I would hand it over to Soumya.
Okay. Am I audible to people? How about now? Better? Okay. For an example of training your first neural network, we will look at the data set MNIST. Most of you are probably familiar with it. It's one of the easiest to learn and fastest data sets that is used in most deep learning tutorials. And MNIST is basically a large database of handwritten digits. There are about 60,000 training images and about 10,000 test images. These images will fall into one of 10 classes, basically digits between 0 to 9. You can see some examples here. And so our input for the network will be 28 cross 28 images, and the output will be one of the classes from 0 to 9. We'll be going through this, we'll be stepping through this notebook line by line, so feel free to stop me anywhere where, if you have a doubt. After we import the necessary libraries, we will first start with downloading the MNIST dataset. So here, train contains the train dataset, and test will contain the test part, because we'll set the parameter train to false to get the test dataset. Transform is a parameter here that can be used to mention the kind of transforms that are to be applied on the images in the dataset. Here, the only transform that we are using is transforms.toTensor, but actually there are a variety of transforms that you may want to use based on your task. You may want to normalize your images, convert them to grayscale, and so on. Once you obtain your train data, for the purpose of this task, we first convert it to NumPy and perform a few visualizations and also print out a few statistics. So you can see that the shape is 28 cross 28, and that you can see what the variance min max of these values is, and so on. This is to visualize a few samples from the trained data set. And now we come to writing the data loader. So Pytorch does provide dataset and data loader classes, which you can use directly. In this case, you could have used the dataset probably directly, but we just wanted to show you how to write your own dataset class to override Pytorch dataset class. For writing your dataset class, you just need to implement two methods, which is length and getItem. Length is to return the length of all the samples in the dataset, and getItem will return each of those samples individually based on the index. The data loader will then batch these samples together and give it to you inside your training loop. So here, to your dataset class, you will be passing your train data and train labels that you obtained previously. And in the init function, you will just probably want to initialize the variables with the labels and the data. And the length function is straightforward. You just return the length. And getItem, in this case, we will want the data to be in float format, because it consists of grayscale images and each value is between 0 to 1. And the labels or the targets are between 0 and 9, and they are discrete, so they are in the format long. This is important finally when you compute your loss, because it will expect the targets to be discrete in this case, and that is why you convert it to long. And then you return both the data and the labels as a tuple. For your data loader, here you can see that we've used Pytorch's data loader. Once we get the data set using the myDataset class that we just wrote, in the arguments you pass in your Yeah, first in the data loader, the first argument is your data set, and in the rest of the arguments, you need to mention whether you want the data loader to shuffle through the data set. So typically when you are training, you want the data to be shuffled at each epoch, because you do not want to pass the data to the network in the exact same sequence. This will hamper your learning. You will see the exact details in the lectures that are to come. And then you pass in your batch size. In this case, it's 256. Number of workers is how many processes you want while loading your data. This data loader tends to parallelize this process so that while your network is running, it already starts loading the next batch and so on. Usually, it is number of workers is 0 if you are not using a GPU on that machine. Otherwise, it is kept between 2 to 8, depending on the number of GPUs you have available. And when you write the arguments for your test loader, you will want to keep shuffle equals false, simply because you do not have to shuffle your test data each time after every epoch. You might as well just pass it in directly. And if you want to visualize some of the samples, it becomes easier if you're not shuffling it. Any questions so far? Okay. Now we'll define our neural network model. This class has to inherit from NN.dot module, and it will have an init function and a forward function, which is called by default. You do not have to mention dot forward for the forward pass. After you call the init function and the super function, you will have to define your layers in the network. In this case, instead of module list, we are using sequential, simply because we do not need any of the intermediate outputs here. So first we have a list, and we append to the list a linear layer followed by an activation layer, which is ReLU in this case. And once we finish appending, so our sequence is linear followed by ReLU, followed by linear and ReLU, and finally a linear layer whose output size will be the number of classes that we want. And after that, this line self.net equals nn.sequential star layers unpacks that list into nn.sequential. nn.sequential actually expects just all the layers listed out, separated by commas. So just using asterisk layers can do that for you automatically. And in the forward function, you just pass the input through this self.net, and you're done. So here, we use the classes that we previously wrote. Model becomes simple MLPs, and the input size is 784, which is 28 into 28. Your hidden size is 256. We are just using one hidden layer in this example. And your output size is 10 for the 10 classes from 0 to 9. The criterion that we are using for loss is cross entropy loss, because we have 10 discrete classes that we want to classify into. Based on your task, this criterion may change. For the optimizer, in this case, we are using Adam. You can also use SGD or any of the other optimizers that Pytorch provides. You can look through the documentation for the exact use and parameters of these functions. And again, because you need to make sure that all your tensors and weights are on the same device, you need to shift all of your data or your models to the device each time. So first, if CUDA is available, then the device becomes CUDA, otherwise it's CPU. And then to shift the model, you simply have to do model.toDevice. But to shift inputs or data, you need to write data equals data.toDevice. This is a very common bug, and it's easy to miss. We printed out our model here. As you can see, there's just one hidden layer, and that is followed by an activation, ReLU, and finally, last hidden layer whose output size is 10. This is our train loop. It is important that for every time you train the model, you set model.train, and every time you are evaluating the model, you use model.eval. This is important because the model might have to perform slightly different tasks in layers like batch normalization. And so if you do not do this every time, you may get wrong results. We initialize our loss to 0 and enumerate train loader or test loader. In this case, will give you the batch index and also the tuple of your data and target that you are returning from your data set, basically, in the dataset class. Only it is batched this time according to the batch size that you provided in the data loader arguments, which is 256. Once you get your data, you will be shifting them to device, and then once you have them on the right device, outputs is just model data. You do not have to explicitly mention dot forward. And loss, again, is straightforward. It's between outputs and target. And running loss, so running loss just maintains a cumulative sum of the loss across all the batches. You want to do dot item because it is a tensor, and this will return the value in it. And loss.backward computes the gradients with respect to all the parameters in your network. And optimizer.step actually takes a step in the direction opposite to all of those gradients. Again, because these gradients are cumulative, it is very important that you do optimizer.zeroGrad each time inside the batch loop, like for every batch. This is important because you are taking a step for every batch. So before that, it is important that the gradients are all made 0. Yeah, the final loss will just be the cumulative sum of the losses across the batch divided by the number of batches that we had. And finally, it's divided by the total number of samples that we had. And finally, you'll print out all your loss and the time taken for your loop. The next function is to test your model. It's very similar to the train loop, except you will not be doing loss.backward, and there is no optimizer which you need to step using. And finally, after you get the outputs, you find the predicted class using torch.max. You take the maximum along the first dimension. And again, you can calculate the accuracy by knowing the total number of predictions and the number of predictions which match the target exactly. Do not forget that these are tensors, so you will have to do something like dot item or dot data to actually get the data in the tensor. Finally, similarly you take a cumulative sum of all the losses across all the batches, and you print out the accuracy and the testing loss. We will just train our model for 10 epochs in this example. Here, after each epoch, we save the train loss, test loss, and test accuracy. This is to plot it later for visualization, and then we print out our values at every stage. Finally, to visualize the data, you just use matplotlib and plot it with respect to the number of epochs. You can see that MNIST is pretty easy to train, so the loss sharply decreases within the first epoch, and after that, it sort of slowly decreases. This is the training loss. Similarly, you can plot the test loss and test accuracy. You can see that after a point, the test loss starts to increase, and that's probably because the data is overfitting to the training data. And similarly, the test accuracy also starts to, after a while, it starts to decrease for the same reason. And to prevent this, you may want to do a number of things like adding dropout or batch normalization. All of this you will have to do in your first assignment, but you will learn about it in the classes that are to come this week. That's it. Any questions?
Yeah, so that's the end of the recitation. We will have the usual lectures from Wednesday onwards. And from the next week onwards, we would have recitations on Fridays and the lectures on Mondays and Wednesdays. Thank you.
Everybody,